For number 1, we have a carnival ride where someone stands against the wall and then the cylinder turns at this rate. This is the velocity. And then when the floor drops so that there's no longer a normal force pointing up on the person, then he still is staying like suspended in the air. And we are trying to find the coefficient of static friction that's needed so that he does not slide down. So we draw a free body diagram. He obviously still feels a weight force pulling down, because we're assuming this is like on the earth. There's friction that is pointing up that keeps him from just sliding down. And then the force that is pointing to the center is the force of the wall on the rider, so that is the normal force pointing to the center. And if the rider is not sliding down, that means that these two are balanced, so my force of friction is equal to my force of gravity. We find force of friction is mu Fn, force of gravity is mass times gravity, which would be 10 as long as we're on Earth. And then the biggest mistake people make here is they try to put Fn is mg. That's not the case here. The normal force is the wall pushing into the center. The normal force is our centripetal force. So my normal is my centripetal force, which is mv squared over r being the radius of this cylinder. So now we're going to substitute this in for Fn. Mu m v squared over the radius equals mass times gravity. Here the masses cancel out. We're trying to solve for mu. So that's mu is gr over v squared. And now we can plug in our numbers. So g was 10, the radius is 4, and then velocity was 18.8 squared. So 10 times 4 divided by 18.8 squared, that gives me 0.113. So then your answer is C, 0.11. That would be the coefficient that is just enough to balance out the force of gravity with a normal force when it is going at this speed. 2, a child whirls a ball at the end of the rope in uniform circular motion, which of those following statements is not true. The speed of the ball is constant, that's true. The velocity of the ball is constant, that is not true. And the reason why is because velocity includes direction. So if I am including the direction and the direction is changing, then the velocity is also changing, not constant. Radius should be constant, the magnitude of the acceleration is constant. So the reason D is true is because it says that magnitude. Magnitude means just the size, not including the direction. So the direction of the acceleration is changing, but the magnitude of the acceleration, however fast, like 5 meters per second squared, that is what's staying constant. Equilibrium means that you have balanced forces, so no acceleration. It can be moving, it just can't be accelerating because the forces cancel out. You have no net force. A satellite moving around the Earth in circular orbit at constant speed. It is going at constant speed, but in order to go around in a circle, you have to have a centripetal force to pull it into the center, to constantly be changing its direction. So that is not equilibrium because it does have a net force. It has a centripetal force. It is accelerating. It's accelerating at v squared over r. But even though my speed might stay the same, you still have an acceleration to turn. Rolling down a frictionless incline would definitely accelerate down. Apple falling obviously accelerates with g 9.8. Going at a constant velocity, yes, that would be equilibrium. A stone of mass m is attached to a strong string and whirled around in a vertical circle. Keyword vertical, meaning it's going up and down. So at the top of the tension, or top of the path, the tension is 3 times the stone's weight. So let's first draw our free body diagram. We obviously have the force of gravity because it's a vertical circle. And then we also have tension down. So my centripetal force, think of centripetal as like my net force, but for a circle. So my centripetal would be the two of these together, the force of gravity and the tension. Force of gravity is just mg. And it says specifically the tension is 3 times the stone's weight, so that's 3, the weight, 3 mg. And that would be my centripetal force. Centripetal force is mv squared over r. 3 mg plus mg is 4 mg. The masses cancel out. We're trying to get the speed or velocity, so I multiply the r up, and then we have v squared is 4gr. we're going to take the square root. Now, square root of 4gr is not an answer choice, but when we take the square root of 4, that just becomes 2. So 4 can come outside of the square root. It's a 2. G and R are not perfect squares, so they have to stay inside. So A, 2 square root of gr. 5, deriving an equation for the orbital velocity around the planet. What are the only things velocity depends on? So orbital velocity of a satellite. So if we talk about like a satellite going around a planet, the only force acting on that satellite is the force of gravity. And the force of gravity is not pulling it down, it's pulling it to the center of the planet all of the time. So that means my centripetal force is the gravitational force, because there's no other forces. So my centripetal force is the force of gravity in this case. So mv squared over r equals, now force of gravity is mg, but little g depends on things, right? We only know little g for the surface of the Earth. We don't know it for around a different planet at a different radius. So instead of using m little g, let's use the force of gravity equation that's true for all planets at all distances. And then we are solving for velocity. So one of the masses cancels out. One of the radiuses cancels out. So I have v squared is gm over r. So then v is square root of gm over r. That would be my velocity equation for something orbiting around a mass, in this case a planet, etc. So the only thing it depends on is the mass of the planet, because the mass we canceled out was the mass of the object or the satellite. So we only care about the mass of the planet, or the thing that it's orbiting around, and the orbital radius. Now, careful here, the orbital radius is not necessarily the radius of the planet. So in this case, if we're talking about like the moon orbiting the Earth, the orbital radius is from the center of the Earth to where the moon is. So that would be how high above the Earth it is, plus the radius of the Earth, etc. So that is the orbital radius. So the circle it orbits in all the way to the center. Which of the following would increase the magnitude of the gravitational field intensity? So gravitational field strength is little g. Little g is the force of gravity over m that's given on our equation sheet. Force of gravity is big G, m1, m2 over r squared. If you divide by m, then one of the m's canceled. And we're left with just gm over r squared. And this is again the mass of like the planet, or the mass of the, I'm going to call it the planet, because in this case it is the planet. It doesn't have to be a planet, but it's the mass of the thing that is creating the gravitational field. So if we're talking about me on the Earth, my mass does not change the gravitational field strength of the Earth. The Earth is going to pull at negative 9.8 or 9.8. No matter what my mass is, all that matters is the mass of the Earth and how far away you are from the center. So we want to increase the mass because we want to multiply by bigger numbers, not the mass of the object, but the mass of the planet. And we want to divide by a smaller number to get a bigger g, so decrease the separation between the object and the planet. Satellite B is 3 times more massive than satellite A, but orbits at 3 times the distance. The gravitational force between A and the planet is F. What is the gravitational force between the planet and B? So we are looking at the force of gravity equation. And this one has 3 times the mass, so only one of the masses, right? Think of like M1 would be like the planet, and then M2 would be like the satellite. So we already know for satellite A, the force is F. Now we're looking for between the satellite B and the planet. So G, same mass of the planet, but now 3 times the mass of the satellite, and 3 times the distance, but distance gets squared, so that's 3 over 9, so it's 1/3 smaller than the force between A and the planet, which was F, so it's just 1/3 of F. Satellite A orbits at a speed of v. What is the speed of satellite B? Well, we just derived on the front that the orbital velocity of a satellite around a planet is the square root of gm over r. Now, most people get tripped up because they put 3m right here, but this is the mass of the planet. So the planet hasn't changed masses. Yes, satellite B has 3 times the mass, but the mass of the satellite does not matter, right? That's the mass we canceled off, so we don't care about how heavy or light the satellite is. All that matters is the mass of the thing it's orbiting around and how far away it is. So we can cross off, if you're not even sure how to do this, well, we can first cross off when you get farther away, then it would be slower. So we can cross off these three, so that's getting faster, and we know it would be slower farther away. And now we just plug in what 3r would do if I keep everything else the same. That's a factor of 3 on the bottom, and most people go to put a, but it is getting square rooted, so this is a factor of 1 over the square root of 3. And if you're like, wait, but why is the 1 not inside the square root? Well, it is, but the square root of 1 is 1. So 1 over square root of 3. So v over square root of 3. Spacecraft X has twice the mass of spacecraft Y. They orbit at the same radius, which the following is true. First is asking about gravitational force. Gravitational force is G m1 m2 over r squared. So both the masses matter, the mass of the Earth and the mass of the spacecraft. So if spacecraft X has twice the mass, then yes, it would feel twice the force. So A is true. Now it's talking about how fast it goes and how long it takes. So that's talking about V, square root of gm over r. Now the only difference between them is the mass of the spacecraft. This is the mass of the planet, which is just Earth's mass. So the mass of the spacecraft would not affect V. So it would not go twice as fast. They would go the same V. And then the period, well, the time it takes is just 2 pi r over the velocity. If this is the same and it's the same radius, then their periods should be the same. So it would not take any longer because it's going equal speed for the same distance, so the same period. 10, we've got a planet with a triple the radius and twice the mass on Earth, gravitational field strength. Oops, didn't mean to cross that off. That's talking about little g. We said on the front, little g is just gm over r squared. It is like your force of gravity, but divided by little m, so the second m cancels. That means the gravitational field strength depends on the mass of the planet and how far away you are from the center of the planet. So this planet has triple the radius, so 3r, and twice the mass of Earth. So that's times 2/9 gm over r squared, where this is little g for Earth. So 2/9 times little g of Earth, which is just 10, gives me 2.22. And technically it's meters per second squared because we are talking about little g, right? The acceleration due to gravity. That means the same thing as the gravitational field strength. Or you can call it Newton over kilogram because we divided a force by a mass, but it doesn't really matter. 2.22. All right, 11, we have twice the mass but half the acceleration due to gravity. So think about it, if it has more mass but less acceleration due to gravity, so less pull, that must mean that you have a bigger radius because you're farther away. So we can only cross off E, but that's okay. Crossing off 1 is good. And we have twice the mass, and we're still talking about the gm over r squared because acceleration due to gravity is just little g, so the same equation. Twice the mass, and we're wondering what happens to the radius in order to get half the acceleration due to gravity. So to get 1/2 of gm over r squared. So let's think about, we have 2 over what gives me 1/2? Well, you want 2 over 4, so that means that you have to double radius because the radius gets squared, which would give me 2/4, which would become 1/2. So 2 times the radius, d. A planet has 3 times the radius of the Earth and 9 times the mass. Acceleration due to gravity, that's little g. That would be a factor of 9 over 9, which means times 1, so it stays the same. So it would be the same on Earth, so little g on Earth is just 10. And same on this planet, because it's the same. 2 planets have the same surface gravity, so they have the same little g, so same little g. Planet B has twice the mass of planet A. If planet A has a radius of r, what's the radius of planet B? So let's think about, we have gm over r squared, and we have g twice the mass. We're looking for how this guy's radius would be affected in order to get the exact same thing back out, because it says they have the same little g, the same surface gravity. So that means you want 2 gm over 2r squared, so that just cancels out. Now we can't put a 2 here, because if we put a 2 here, that becomes 2 over 4, 1/2. So what you would put is square root of 2, because when you square that, see how that gives you a factor of 2? That would then cancel out and give me the same surface gravity as the other one. The 2 spheres have equal density and are subject only to their mutual gravitation attraction, gravitational, so they are going to feel force of gravity towards one another. Which of the following quantities must have the same magnitude for both spheres? They would not have the same acceleration because the smaller mass would have a much greater acceleration than the bigger mass. Velocity, I don't know anything about whether they're moving or not, so I don't know anything about their velocities. Inertia is like their mass. This one obviously has much more mass if it's equal density and much bigger size. Their gravitational force would be the same because your gravitational force is g m1 m2 over r squared. It doesn't matter which one's your m1 and which one's your m2. If you're saying this guy and this guy versus this guy and this guy, it's the same force. It's also Newton's third law, equal and opposite. If we are talking about the force of this one on this one and the force of this one on this one, that's the same force, the force of gravity. Now, this one actually moves because it feels the same force, but a much smaller mass, so a bigger acceleration, but it's the same force. Two identical planets orbit a star in concentric circular orbits. The planet that is farther away, and it's talking about speed and velocities, so your velocity is like this. If this is greater, then dividing by a bigger number gives you a slower velocity, slower v. And if it's going slower, that would mean a longer period. So we can cross off shorter period. That's not true. It would take longer because it's going slower and it has a greater distance. If it's farther away, slower velocity, yes, we decided that was true. Larger acceleration towards the star, so acceleration is v squared over r. This one is less and it's farther away, so this one is more. If you decrease it and divide by a bigger number, then it's getting smaller and smaller, so it's not larger acceleration. Universal gravitational constant, that's big G, that's always the same, and constant means constant, so can't be larger. Satellite B has 3 times the mass of satellite A, and they're traveling, which one travels at a faster speed? So speed depends on the mass of the planet and how far away you are. Orbiting the same planet at the same radius, so they travel at the same speed. Mass of the satellite does not matter for the speed. Centripetal acceleration would be v squared over r. We just said this is the same and your radius is the same, so this acceleration has to be the same. Gravitational force is big G m1 m2 over r squared. This is not the same because the gravitational force depends on the mass of the Earth, which is the same, how far away they are, which is the same, and the mass of the second object, which is not the same. So the greater gravitational force would come from the greater mass, which is satellite B. And it would be 3 times the force because you have 3 times the mass right here. A hypothetical planet has a mass 9 times that of Earth, but the same gravitational field strength, so the same G. So we have G, 9 times the mass. What do we do to R in order to get just G out? So if you have 9 on top, you need a 9 on bottom to cancel out. So 3r squared because that would square and get 9. So 3 times the radius of Earth. Swung in a vertical circle at a constant speed. The mass of the sphere is m and the radius is r. The position is marked or recorded. Sketch in the acceleration vectors. For something moving in a circle, your acceleration is always into the center, like this. Draw a free body diagram. So at point 1, we have both the gravity and the tension pulling down. 2, it is gravity obviously down and tension is to the left. At 3, tension is pulling up and there's still the force of gravity down, so tension must be greater here because I still accelerate up. And then at 4, we've got tension into the circle and force of gravity down. Give an expression for the tension in the rope at 1, 2, and 3. So at 1, your centripetal force is the 2 of these together. Remember, centripetal force is like your net force. It's just specifically the net force for something going in a circle. So your tension plus mass times gravity equals mv squared over r. Get tension by itself, you subtract over. So mv squared over r minus mg gives me the tension. At point 2, so here the gravity and the tension are actually perpendicular to each other, so they don't affect one another. So here my centripetal force is just my tension. So my tension is mv squared over r. And then this is for 1, this is for 2. And at point 3, So at point 3, my net force is tension minus gravity because they're going in opposite directions. So Fc is T minus mg. So then mv squared over r, add the mg over, gives me my tension at 3. And I said that tension would be greatest at 3, and it should be the least up here because gravity is helping that tension, whereas here gravity is going against the tension. And that makes sense because here gravity is greater, not gravity is greater, tension is greater because you're adding mg. Here at point 1, tension is less because you're subtracting mg. And here your tension is just your centripetal because the gravity isn't adding or subtracting to the tension force. The radius of Mars is half that of Earth's, and the mass is 1/10 that of the Earth's. And which of the following is closest to gravitational field? Well, gravitational field is little g, that's gm over r squared. So that gives me 0.1 over 0.25, which gives me times 0.4. Now that is the factor of how much smaller it's getting, and that's compared to Earth, because this is all in terms of Earth's mass and Earth's radius. So if it's 0.4 smaller than Earth, and Earth's is 10, then 0.4 times 10 gives me 4 newtons per kilogram. At the top, it says it's going around like counterclockwise like this, so your velocity would be going to the left, and your acceleration always has to point straight into the center, which in this case is down, so B. At the highest point, so the highest point, it feels the force of gravity and it feels tension, and that's what's causing this centripetal acceleration. So the centripetal force is just tension plus the force of gravity. I'm looking for tension, so that's Fc minus mg. And normally we would do mv squared over r, but it's not in terms of v squared and r, but centripetal force is just mass times acceleration. It's specifically the centripetal acceleration. So this is the same as mv squared over r equal or minus mg, because AC is v squared over r, like it says on your equation sheet. So just C. We're finding the gravitational field strength of each planet. So gravitational field strength is little g, that's gm over r squared. Twice the mass and half the radius would give me 2 over 1/4, which is times 8. And that is times 8 of Earth, because it's in terms of Earth's mass and radius. Gravitational field strength on Earth is 10, so 8 times 10 gives me 80. Y has half the mass and twice the radius, so it's less mass and farther away, so it should be a much smaller gravitational field. That gives me 1/2 over 4, which is times 1/8. Times 1/8 smaller than Earth's. Earth's gravitational field strength is 10, so 1/8 of 10 gives me 1.25. So that would give me 1.25 for planet Y. And then lastly, planet Z, twice the mass and twice the radius. That gives me times 1/2. 1/2 of Earth's, which is 10, gives me a gravitational field strength of 5 then. Planet Q has 8 times the mass and a gravitational field strength of 5, so that's 1/2 of Earth's gravitational field strength. So I have 8 times the mass, and I want to know what I need to do to the radius in order to end up with 1/2. So to get 1/2, I've got 8 over, that must be 16 to get 1/2. That doesn't look like an 8. And if I want 16 on bottom, that means 4 times the radius because it would get squared. So I need 4 times the radius of Earth. 2 satellites with a mass of m and a mass of 2m orbit the same planet of mass big M at the same height. The orbital velocity of x is v, and the orbital velocity of y is still v, because velocity depends on 2 things. Mass of the planet, which is the same, and the orbital radius, same height, same radius. So that satellite being greater mass doesn't affect the velocity, it doesn't affect the acceleration, it doesn't affect the period. The only thing that second mass would affect is the force of gravity, because that has m1 and m2 in it. 27, a satellite travels around a planet at this speed and this radius. What would the speed of an identical satellite orbiting at 1/4 this radius? So Here, we actually don't need to plug in like these numbers because we don't know the mass of the satellite, so we don't need to like find the mass of the satellite. We just want to know 1/4 the radius, what happens. So think about if I'm at some radius and I go 1/4, we know that closer would have to go faster, so we can cross off these two because that would be going slower. That's going the same speed, and I know it needs to go faster. Now the question is how much faster, so our equation, if we plug in 1/4 the radius, well, that would be like 1/1/4, which is 4. But it's inside of a square root, so that would actually be 2 times faster. And then now it's, okay, this is my old velocity, times 2 gives me 1.8 times 10 to the 4th. Two objects orbit the same sun. The first object follows a circular path with a radius r and an orbital velocity v. Second object orbits at a much bigger radius. So we know whenever you are going farther away from the sun or whatever you're orbiting, then you need to go slower to stay in that orbit because you're much, much farther away. So we can cross off that. Oh, that's good. Cross off. Cross 3 of 5 off. Because we know that it needs to be slower, so less velocity, not more. And then now to find out how much, we have to actually plug in what 25r would do. That would be a square root of like 1/25, which is then like 1/5 the velocity, so v/5, 1/5 the velocity. Satellite in a circular orbit, in a lower altitude. So if I have going around like this and now I go to a closer altitude like this, whenever you go closer, well, let's look at our equation. So gm/r, if this gets smaller, well, when you divide by a smaller number, then that makes this get bigger. So it's going to go faster, so we can cross off a and b. And then you can think about your equation for period, 2 pi r/v. And we said that this is smaller, and this one would then be bigger. You're multiplying by a smaller number, dividing by a bigger number, this gets smaller. So a greater speed and a shorter period. You also could just say, okay, if it's going faster and it has less distance to travel, because this is a smaller circle, then of course it takes less time. So see?